Okay, so now we're going to talk about what are called liftings. And basically, what's going to happen is that we're going to relate the construction of a, it's like a Voronoi, it's like a diagram in sort of RD, is like with a lifted version of it in RD plus 1. And the lifting is going to involve stereographic projections and sphere inversions. Okay, so Voronoi diagrams can be understood by lifting cells to one higher dimension by using the inverse stereographic projection. Okay, and the way, of course, we do this, it's like, if you recall, is that we first embed, it's like RD into RD plus 1. Okay, so we embed RD into RD plus 1. It's like where x just gets mapped to x comma 0, right? So the last component, the d plus first component, is just set to 0. Okay, and we map each point u in this set S, right, to the d-dimensional sphere using the inverse stereographic projection. And let pi u, right, be the d-plane that is tangent to SD, right, at the preimage or the inverse of the stereographic projection applied to u. Okay, so let me try to draw for you, it's like what's happening in pictures. So what I'm going to do is that I'm going to think of just this line here as RD, right, and then the whole space is RD plus 1. Okay, so this is the point where it's like all the data lives, it's like all the S's live, it's like in this codimension 1, it's like hyperplane. Okay, and then if you recall, you have stereographic projection, which involves having this sphere. It's like with a north pole here. All right, and so what is going to happen is that if you have a point U and a point V on RD, right, these are going to be mapped by the inverse stereographic projection to points, let's call that, it's like S inverse U and S inverse V, right? Okay, and then the point is that there are tangent planes to this, okay, which I call pi u and pi phi. So this is where we're at right now, right? So we have points in RD, we have the sphere, it's like which is used to define stereographic projection, okay, and we have the inverse stereographic projection, which maps u, it's like to this SD, okay, and then we have the tangent planes, which are tangent to that sphere. Okay, so now you have these planes, okay, and then we're going to apply an sort of sphere inversion, okay, about again about it's like this North Pole, okay, in order to map these back to spheres. Okay, so using sphere inversion, right, pi u and pi v, right, map to, let's call that sigma u, which is the inversion applied to pi u, right? Okay. Right. Yes. Okay. And okay, so essentially what's going to happen, if you recall, is that, okay, so there's some ups. Okay. So this diagram's a little bit off. So let's see. Okay, so I'm not doing a great job, but the point is that where these two spheres intersect, one of them is always at the north pole, because essentially what happens is that the points at infinity, it's like get mapped to the center of the sphere, right? So so it gets back to the north pole, and then the intersection point, it's like gets mapped to this point here. Okay, so so in any case, it's like the ray from the north pole, it's like to the intersection point will you know, will reach out to this intersection between the two hyperplanes. Okay, all right. So anyway, so you have these pi u's and pi v's, which are obtained by sphere inversion of these hyperplanes, which are tangent to the sphere. It's like at the point where sort of the inverse stereographic projection maps the point v, it's like to the d sphere. Okay. So these two spheres you get, right? So this is what I call pi u and pi v, right? So these two spheres have two properties, right? So they go through the north pole. N, right, and a tangent to RD. Okay, and then that's because RD is the pre-image of sort of this SD by the sphere inversion, which defines the stereographic projection. So I should say that all the sphere inversions we're talking about, right, are the ones it's like which were used to define the stereographic projection, right? Which means that it has a center, it's like at the north pole, it's like and stuff like that. Okay, so all right, so it's fairly clear that it goes through the north pole, because again, it's like infinity gets mapped to the north pole, which is the center of the sphere. And then the other thing basically is that it is tangent to RD. It's like because RD, if you recall, gets mapped to the sphere, right? And this plane, this original D hyperplane, is tangent to the sphere, all right? So essentially what happens is that the sphere then gets mapped to the plane. This hyperplane gets mapped to these circles, and they still maintain this tangency relationship under sphere inversion. Okay, so that's where all of this is coming from. Okay, so once you have this, then we can say something about how you can characterize whether or not a point lives in a particular Voronoi cell in terms of this kind of interpretation. So there is the first sort of sphere lemma. What it says is that a point x in RD, right, belongs to the Voronoi cell VU, right, if and only if the first intersection of the directed line segment starting at x, so from x to the North Pole, right? So the first intersection of this directed line from the point x to the North Pole, right, basically intersects the d sphere associated with the point u of v, right? Okay. With the d spheres defined by the points in S, right, is with the sphere associated with U. Okay. All right. So let's try to prove this. So the proof is as follows. So what you can do is you can interpret it's like these pi u and pi v's, it's like as now weighted points in the sense of these weighted Voronoi duals. And what's going to happen basically is that the weighted Voronoi cells in this high dimensional space, right, intersect the Voronoi cells, it's like on RD, which give the usual Voronoi cells. So there's a relationship, if you will, between weighted Voronoi cells in this larger dimensional space, d plus 1 dimensional space, with the Voronoi cells, it's like in the usual RD space. So I interpret sigma mu as a weighted point. With weight equal to the square of its radius. Okay, so right. So what's going to happen is that there's a center. It's like of this sphere. It's like sigma u, right? And then there is this length. Obviously, is the radius. Okay, and then you have a point. It's like on RD, which is right now it's just this line. Okay, so essentially what happens is the following, right? So you know that we're in Euclidean space, we're in RD plus 1. So the distance between, it's like the center, it's like, and this point, say x on RD, right, embedded into RD plus 1, right, is by the Pythagoras theorem, it's like the sum of squares between this and this, right? So so I have to add the square radius, it's like of that sphere with just the usual distance on RD, okay? But I'm using this weighted, it's like square distance where I subtract the square of the, well, I subtract the weight, but the weight is the square of the radius. So essentially it's like this contribution, it's like from the radius disappears, and all I'm left with, essentially the power of u from the point, sorry, the power of x from the point u, right, is nothing more than the distance squared, it's like in the RD plane between the point u, it's like, and so the point u and x. So I should say not the power between x and u, but the power between x and the center of sigma u, which is sort of what we're doing here. Okay, so in any case, so the point is that there's a relationship between this notion of power in terms of these kind of weighted sort of points, right, with the notion of just the distance, it's like in this low dimensional space. Okay, so the point is that, yeah, so the power of x, right, is the square distance, the square length of a tangent line segment, okay, which is just sort of the norm squared of x minus u, okay, if, at least if x is in RD, right? And again, every time I say RD, I really want to think of it as being embedded in RD plus 1. Okay, so so the bottom line then is that so the weighted Voronoi cell of the weighted center sort of intersects RD in the Voronoi cell of U. Okay, so these weighted, it's like Voronoi cells, it's like which is in RD plus 1, it's like intersect with RD with the usual Voronoi cells. Okay, and then the other observation is that all bisectors of the weighted points pass through U, pass through the North Pole, right? And then basically, again, this first sphere lemma says that you go from this point X, it's like to the North Pole based on where you intersect first. It's like whether it's this sphere or this sphere, right? Then you're either, you know, it's like the left or right, if you will. It's like of the bisector, okay? And again, the way to sort of think about this is that you're you're sort of going, it's like from the point in some appropriate sense, it's like, you know, back to, yeah, so again, it's like you can see that the bisector here, right, separates, it's like the weighted, it's like Voronoi cells in the higher dimensional space. So based on, you know, where you intersect first, it's like you'll be able to tell, it's like whether you're to the left or right of this bisector. So that's the statement of this first sphere lemma, okay? And then there's sort of a similar result. It's like where instead of working, it's like with these spheres, it's like pi u and pi v, you can work with these hyperplanes instead. So let me just state that result. And again, it's like the result is in some sense a consequence of the sphere lemma. It's like together with the identifications via sphere inversion. It's like between, again, these spheres and this hyperplane versus it's like, you know, it's like these two hyperplanes, okay? Okay, so this is what is called the first plane lemma. So it says that a point x in RD, right, belongs to the Voronoi cell of U in S, right, if and only if the first intersection of the directed line segment from now the North Pole to X, right? Okay, so this is perhaps sort of easier to see, right? Because you know that the intersection between these two hyperplanes is exactly, you know, the line from the North Pole to the intersection of these two hyperplanes is exactly the bisector in this weighted sense, right? So again, depending on whether you go from the North Pole to X, it's like whether you hit first this hyperplane or that hyperplane, right? Tells you whether you're to the left or right of that bisector. Okay. And you know, when I say left or right, I really sort of mean it in the sense of, you know, which side you're on, right? Okay. Okay. from X, okay, with the D-planes defined by points in S. Right, is with pi u. Okay, so that's sort of a dual construction, if you will. It's like, and you know, the proof is, I mean, perhaps the easiest way, again, it's like to think about it is from the observation that, you know, the intersection between these two hyperplanes, right, is on a line segment, which, so the intersection, it's like of the bisector, it's like between, it's like this weighted bisector between those 2 points is exactly going to go through this intersection between hyperplanes. Okay, all right, so let me just stop here.